The cold was a constant gnawing enemy in the winter of 1943. Not the kind of enemy that bled, but one that relentlessly crippled men and machines. Near the snow-dusted rail lines outside Poltava, a German technical recovery unit, the Burgesog, moved with grim efficiency. Their target wasn't a prize tiger, but a piece of wreckage. A carcass of Allied air superiority. A Republic P-47 Thunderbolt. The sight of it, even mangled, was a chilling reminder of the air war they were losing. American fighters, flown by men they dismissed as farm boys, were proving brutally effective. The P-47, in particular, was an airborne brute. A monster of an aircraft built around one of the largest, most powerful piston engines ever made. The Pratt & Whitney R2800 double wasp. The Germans knew the P-47's reputation. A jug that could dive faster than a Stuka, absorb more punishment than any FW-190, and, crucially, deliver sustained firepower from its 8.50 caliber machine guns. But for the engineers and mechanics of the Burgesog, the P-47 represented an enigma. How could such a massive engine, generating well over 2,000 horsepower, operate reliably in a fighter chassis without cooking itself alive? German engine cooling systems were complex, often fragile, and a constant point of failure. The P-47, however, seemed to simply ... run in the furious, high-stakes arms race of World War II aviation. Thermal management was the true, often unseen enemy of performance. Every engine generates heat, and in a massive radial engine like the R2800, that heat was immense. Pushing a fighter to maximum speed or engaging in prolonged combat required the pilot to constantly manage the engine's temperature. Overheat the cylinders, and you risk pre-ignition, detonation, or outright engine seizure. For the Luftwaffe, this issue was critical. Their premier fighters, the Messerschmitt Bf-109 and Focke-Wulf FW-1090, both relied on complex, often vulnerable liquid cooling systems, Bf-109, or tightly cowled radial engines. FW-190 that, while sleek, often sacrificed sustained high-power output for aerodynamic profile. The P-47 was different. It used an air-cooled radial engine, a design choice the Germans had largely abandoned for their high-altitude fighters. To move enough air to cool the beast of the R2800, the P-47 should, by all logic, have had an unacceptably large frontal area, making it slow and clumsy. Yet, it wasn't. Its engineers had somehow cheated physics. The captured wreck was a chance to see that deception up close. Oberleutnant Klaus Richter, a wiry, precise engineer who headed the Burgesog detachment, viewed the wreckage not with anger, but with intense academic curiosity. He and his team were here to strip the fallen giant of its secrets before Soviet hands claimed it. The first inspection of the engine cowling yielded nothing revolutionary. The familiar array of adjustable cowl flaps used by the pilot to regulate airflow were present, but they weren't the answer. Any German engineer could design cowl flaps. The problem lay deeper, within the structure that encased the engine and the eight thick-barreled machine guns mounted in the wing. "We need to get into the wing route, Hans," Richter commanded, pointing toward the massive, fillet-like juncture where the wing met the fuselage. "The carburetor intake is there. See how the ducts run back." The team began the painstaking process of removing the aluminum panels. American manufacturing was brutally efficient, utilizing simple spot welds and machine screws. A contrast to the often overly complex, hand-fitted assemblies of German aircraft. It was a philosophy of mass-produced ruggedness. Finally, with a grinding screech of protesting metal, a large inspection panel on the underside of the port wing was removed, revealing the engine accessory section and the internal ducting. What they saw immediately was not a mass of pipes and pumps, but an unusual pathway for air. Air entering the massive main carburetor intake at the front of the fuselage didn't just go to the engine. A portion of it was being routed or tapped into a secondary system. This secondary airflow vanished deep inside the wing root, snaking its way past the intricate ducting for the turbo supercharger, the other technical marvel. The Germans envied. This was where the typical German design would have employed heavy, insulated piping and complex valve systems to draw air for the oil cooler and intercoolers, using a separate, often drag-inducing inlet. But here, the American design seemed to rely on a single, shared source, yet achieve unprecedented thermal stability. As Hans cleaned away oil residue and bent down for a closer look, he saw an unusual, segmented internal baffle just behind the main intake duct. It wasn't a typical splitter or a valve. It was a simple sheet metal barrier designed to accelerate and redirect a portion of the incoming high-pressure ram air. It was positioned just so to exploit the physics of the airflow, not fight it with mechanical complexity. Richter traced the path with his finger. The air is entering the system, moving past this baffle and being split. But where is it going? They could see the inlet. The exit, however, was a mystery. It had to be exhausting somewhere low pressure, perhaps out the belly of the plane, but the piping was simple, almost crude. It didn't look like an intricate German-designed cooling system. It looked like a brilliant trick. The captured P-47 hadn't just crashed. It had landed on a vital, unsolved engineering secret. The wreckage, or at least the critical engine and wing sections, was carefully crated and transported hundreds of miles west to a dedicated Luftwaffe research facility outside Rechlin. This was the nerve center where Allied technological gains were analyzed, reverse-engineered, and, ideally, copied. Oberleutnant Richter, now elevated to leading the analysis team, was eager to prove his worth by solving the Jug's cooling mystery. The first few days were spent in pure dissection. They removed the R2800 engine, a masterpiece of American mass production, and placed it on a stand. Its cooling fins were deep and numerous, but the Germans had engines with similar finning. The true focus remained the ductwork revealed in the wing root, the internal bypass system. The initial theory among the senior engineers, men steeped in the complex physics of German aircraft design, was that the Americans must be using some form of ejector cooling. This technique, involving venting engine exhaust gases near the cooling air outlet, creates a low-pressure area that sucks cooling air through the engine more efficiently. It was a known principle, but applying it to the P-47's design seemed inefficient given the size of the air inlet. Richter, however, was skeptical of the complex answer. "Look at this," Richter told his colleague, Dr. Voss, a civilian aerodynamicist. He pointed to the simple metal divider they had found the internal baffle. "This piece, it's too crude to be part of a fine-tuned ejector system. It looks like it belongs on a plumbing fixture, not a high-speed fighter." Voss and his team began the arduous task of creating a precise, full-scale drawing of the P-47's internal layout. German engineers were accustomed to dealing with tight tolerances and meticulously detailed blueprints. The P-47's plans, however, revealed a baffling lack of precision in areas they considered critical. The cooling ducting, in particular, seemed to employ wide, smooth curves and almost casual transitions, not the mathematically optimized, sharp-edged channels they would have mandated as they meticulously measured the area of the ducting at various points. A pattern emerged that made no sense. The channel that fed the oil cooler and intercoolers, the air-to-air heat exchangers that cooled the compressed air, heading to the engine didn't decrease in area as sharply as they expected. German design principles dictated minimizing internal volume to keep air moving quickly. But the American duct seemed to hold a larger volume of air for a longer path. "It's like they're trying to slow the air down before it hits the coolers," Voss muttered, tapping his pencil against the diagram. "But if the velocity drops, the cooling effectiveness drops. This is structurally unsound. The engine must overheat in a sustained climb." Richter arranged for a replica section of the ducting to be fabricated, a costly and time-consuming process. They then mounted it in the facility's low-speed wind tunnel, a tool normally reserved for testing wing profiles, not internal plumbing. Their goal was to measure the pressure, recovery, and mass flow rate through the system. If the German theory of fluid dynamics held true for this geometry, the system should show poor efficiency. The turbulence created by the simple baffle would cause a massive pressure drop, choking the coolers and leading to inevitable failure at high power settings. The results, run over several days, were bafflingly consistent. The ductwork, despite its apparent crudeness, achieved an astonishingly high-pressure recovery. The air flowed through the snaking channels past the heat exchangers and out the rear exit without the expected parasitic drag or turbulence. It was as if the air itself was cooperating with the design. "It's not just the shape," Richter concluded during one tense review meeting, pointing at the schematics. "It's the placement. That baffle is positioned to take advantage of the high stagnation pressure built up in the main intake." One evening, while reviewing the sectioned panels under a harsh workshop lamp, a young mechanic named Werner noticed something that PhDs had overlooked. He pointed to the interior surfaces of the ductwork, which in German planes were often meticulously polished or even painted to reduce skin friction. "Oberleutnant, the inside," Werner said hesitantly. "The surface is rough. It looks stamped, not finished." Richter and Voss bent closer. The internal aluminum surface was indeed slightly corrugated, the result of a high-speed mass-production stamping process. It wasn't smooth. The German engineers had been painstakingly polishing their prototypes, believing that a perfectly smooth internal surface was paramount for efficient airflow. But what if the slight roughness of the American manufacturing process was actually the secret trick? The rough surface, Werner theorized, wasn't a flaw. It was a feature. In complex ducts, a slightly rough surface can actually promote the formation of a thin boundary layer of air that acts like a lubricant, preventing the main high-velocity air mass from separating from the inner duct wall, thus preventing the dreaded turbulence. The Americans hadn't designed a complex system. They had simply leveraged the results of their assembly line pragmatism, a design born not from theory, but from the brutal efficiency of the factory. Richter felt a cold sweat. It was simple, genius, and entirely accidental lore, so it seemed. The true solution lay somewhere between high-level physics and the speed of the assembly line. And they hadn't found the exact combination yet. Richter realized the German methodology was flawed. They were trying to solve the problem with complex, bespoke solutions, while the Americans had found a simple, powerful application of fundamental physics. This wasn't about refined metallurgy or intricate valves. It was about the manipulation of airflow velocity and pressure recovery using basic geometry, what became known later in engineering circles as exploiting the Kondak effect. Though the Americans likely stumbled upon the optimization through trial and error, the heart of the solution lay in Bernoulli's principle. When air enters the P-47's large intake, it hits a high-pressure point stagnation point. Instead of forcing all that high-pressure air through narrow, high-resistance coolers as German designs often did, the P-47 design exploited the principle that as air velocity decreases, its static pressure increases. The American ducts were shaped to gradually diffuse the high-velocity ram air. Slowing it down, this subtle deceleration was the key. When the air reached the oil coolers and intercoolers, it wasn't screaming past, fighting the heat exchangers' fins. It was moving with a higher static pressure, literally pressing through the maze of fins more effectively. Higher static pressure means a better driving force for the mass of air through the resistance of the heat exchanger core, dramatically increasing the efficiency of heat transfer without relying on heavy, complex mechanical pumps. Richter used his chalk to diagram the crucial cross-section for Dr. Voss. The airflow area, $Australian dollar, increases. Therefore, the velocity, $V, decreases, and the static pressure, $P$, increases. He wrote the fundamental relationship on the blackboard. $V_1, V_2 implies P_1 greater than P_2, illustrating how the geometry was converting dynamic pressure into static pressure right where it was needed. The second genius element was the diffuser shape and the resulting boundary layer control. The rough, mass-stamped interior surface that mechanic Werner had identified was crucial. A highly polished surface, contrary to their expectations, encourages the high-velocity air in a duct to separate from the inner wall when the duct curve is tight or the air is slowing down rapidly, a phenomenon called flow separation. This separation creates chaotic turbulence, vortices, which causes massive fluid loss and pressure drop. The slightly rough internal surface of the P-47 duct did the opposite. It caused a thin, stable, turbulent boundary layer to form immediately along the wall. Ironically, a turbulent boundary layer is much more resilient to separation than a smooth, laminar one. This thin, resilient layer acted like an invisible guide rail, keeping the main, high-pressure airflow firmly attached to the duct walls, even through the complex curves and the deceleration zones. The roughness, Dr. Voss finally understood, prevents the chaotic separation. It maintains the stability of the entire mass flow. It is a deliberate aerodynamic ducting system, not just plumbing. He ran his hand over the German-made test piece, polished, smooth. We were fighting the air. They are guiding it. This simple feature meant the P-47 could maintain efficient air delivery to its internal cooters with minimal drag penalties, sustaining high engine power for longer, a capability essential for high-altitude escort duties over Europe. The realization was sobering. The Americans had cracked a fundamental aerodynamic problem, not with a $20 million research budget, but likely with a keen-eyed engineer on the factory floor who realized the rough stamping worked while Richter and Voss wrestled with the mathematical realities of the ducting. The intelligence reports from the front continued to paint a dramatic picture of the P-47's resilience. The engineering solution had a direct, terrifying consequence for the German pilots facing them. Hauptmann Dieter Noll, a seasoned expert with over 50 confirmed kills flying the WWII, described his encounters with the P-47 in chilling detail. In a low-altitude dogfight, Noll's WWII was peerless. But at altitude where the P-47 thrived, thanks to its SCLI turbo supercharger, and perfect cooling, the fight was different. Goo! You could push the curt WWII for a quick burst, a climbing turn, and your engine temperatures would spike, forcing you to back off, Noll wrote in his report. But the jug, it would just absorb it. The pilots flew with a confidence we did not possess. They would hold the throttle wide open, sometimes for minutes at a time, pulling away from us, their great engine roaring. We knew that kind of abuse should have seized the engine block, melted the oil. This difference in thermal reliability translated directly into battlefield dominance. The P-47 pilot could choose to fight or disengage at will, while the German pilot was perpetually managing the fine line between victory and noblesse. And noblesse, my only lipstick. Ruby kiss, only ruby kiss. Only ruby kiss has the luxurious texture, my lesk, lied, no co. And noblesse, timey side of my lied, teitsque selles. My lied, while the German pilot was persecuted. My lied, my movie alest. You know we see it, to see it a sped. My mia sef, to be my Mrs. of cad. By subide, to hell with the less ka it says. To me sal, so I could da me boppy sli sid sit I'm si se kep se kata biet sli krika I se lut sitis to kakata butis kesip. Catastrophic engine failure. Richter realized that the cooling mystery was not isolated. It was intrinsically linked to American air dominance. The reliable cooling meant the R-2800 could handle the massive heat generated by continuous high-speed flight, and the immense energy required to drive the powerful turbo super. It meant the Americans could deploy their fighters farther, higher, and for longer duration over German airspace. However, a new threat was now emerging on the Eastern Front that demanded a different kind of technological leap. The Soviet tanks were becoming thicker, and the German panzers were facing a new generation of American-supplied armor-piercing ammunition. This ammunition, the high-velocity armor-piercing HVAP round, utilized a tungsten core technology the Germans desperately needed to improve their own anti-tank efforts. The irony was not lost on Richter. The Americans had solved the thermal management problem of their airplanes with simple ingenuity. Now, the German war effort was about to face a far deadlier application of another material, tungsten, whose effectiveness was directly tied to the ability to generate and manage massive energy. The cooling problem and the emerging threat of HVAP were two sides of the same coin. The engineering race for military supremacy as the cooling riddle of the P-47 continued to frustrate the German engineers at Rechlin. A far more deadly problem was materializing on the eastern and western fronts. The Allied air superiority was only half the battle. The other half was the hardening of enemy ground forces. By 1944, the standard German anti-tank gun, the beloved Pak-40, was struggling to reliably defeat the newest generation of Soviet and American medium tanks, the Soviet T-34 85ths and the American M4. Sherman, when equipped with applique armor or the long-barreled $76 text gun, were proving increasingly resistant to the standard German AP-CBC armor-piercing, capped, ballistic capped ammunition. The core issue was simple physics. To punch through thick, sloped steel, you needed to concentrate an enormous amount of kinetic energy into a small area. The conventional German steel shell, which relied on its mass and hardness, was reaching its effective limit. To improve penetration, the Germans had two options: increase the muzzle velocity by lengthening the gun barrel, which was logistically complex, or revolutionize the projectile itself. This necessity gave rise to the development and, crucially, the capture of a new American projectile that would terrify the Wehrmacht: the HVAP high-velocity armor-piercing round. Known to the Americans as a PCR armor-piercing composite, rigid or sometimes tungsten penetrator, the HVAP round was a complete departure from traditional ammunition. While a standard $75 text $mm round used a steel body of $75 text diameter, the HVAP round was structurally different. It consisted of a core, the true penetrator, made of extremely dense, hard material, often tungsten carbide. This core was much smaller than the gun's bore, perhaps only $37 text in diameter, to allow the smaller core to be fired by a $75 text $mm gun. The core was encased in a lightweight outer sleeve or sabot, a French word meaning shoe or clog. The sabot matched the full diameter of the gun bore and engaged the rifling, ensuring the projectile accelerated cleanly down the barrel. Once the round exited the muzzle, air resistance violently stripped the lightweight sabot away, allowing the dense, small-diameter tungsten core to continue to the target. The result was a revolutionary increase in performance. Because the projectile's mass $M was concentrated in the small, dense core and its diameter $D was minimal, the projectile had a far higher sectional density text SD equals MDA. More importantly, the lighter overall weight of the complete round allowed the gun to impart a much higher muzzle velocity, $V, often $20 to $30 percent faster than standard rounds. Since kinetic energy is proportional to $MCDEY, the increase in velocity was the dominant factor, translating directly into vastly superior armor penetration upon impact. The Germans understood the physics of this design. In fact, they had developed similar projectiles, the PZGR-40 series, early in the war. However, they faced a critical, insurmountable obstacle: tungsten scarcity. Tungsten was essential for hardening machine tools and was vital for their industrial base. With their supply lines strangled by Allied blockade and diplomatic pressure, the German High Command had restricted the use of tungsten for ammunition. The Allies, conversely, had reliable access to large tungsten reserves. When the first German tanks were struck by American HVAP, rounds hitting with a terrifying, almost surgical force, the shock was profound. It wasn't just the penetration. It was the psychological speed. The rounds flew flatter, faster, and hit with a deafening crack. German tank crews were used to seeing rounds spark and deflect off their thick, sloped armor. Now, they were simply being perforated. Richter's analysis team, all focused on the P-47's air duct, was simultaneously tasked with analyzing captured EVAP rounds. The contrast was stark. The American P-47 cooling trick relied on simple, mass-produced aerodynamics, while the HHVE round relied on a strategic material advantage the Germans could not match. The engineers, obsessed with the complexity of the P-47's ducting, had initially dismissed the HVAP as a simple metallurgical problem. But the combat reports told a different story. The appearance of the HVAP on the battlefield introduced an element of paralysis that tank commanders could no longer rely on the armor of their Panther or Tiger tanks to shrug off the enemies. Fire. One report from a Tiger commander in the Falaise pocket was particularly chilling. We engaged an American column, 3 Shermans. The first hit was silent, like a hammer blow. But the round did not explode, simply went through the glass's plate, as if it were paper. The tank brewed up instantly. We recovered the projectile. It was small, polished, and barely deformed. We are now fighting ghost bullets. The German engineers understood the HVAP round required precise, large-scale manufacturing to produce the perfect tungsten penetrator, density and hardness that only reliable mass production techniques could guarantee. Just like the P-47's cooling system, the HVAP round was a testament to the efficient, strategic, and often simple genius of American mass production. The stage was set for a massive confrontation. The psychological confidence of the AHA. The Ruby Kiss, Ruby Kiss. Only Ruby Kiss. Only Ruby Kiss has the luxurious texture that glides on we. AHHA 6th, EHS. And relies a place E-E-S Milest. E-E-Y-Y-Y-E-S-A. EHA-A-S, well, E-F, we see up, there's F, play with C-clad, go a sit, by we and, with Sefa Khan to with a lie gog cret to set it pan it's a walk gat a say to me it is a sick brick I said you klutz stis kitata to see readedly to cola and sits it to the petita. German tankers against the devastating kinetic energy delivered by the Allied tungsten penetrators. The cold, relentless winter that had shrouded Richter's investigation into the P-47 now formed the Agricola Kiss, now formed the backdrop of the deadliest tank battles of the war. During the German counteroffensive, the Battle of the Bulge, the final, desperate gamble of the Wehrmacht, played out in the snowy forests of the Ardennes. Here, the German heavy tanks the Tiger to Königsdegger and the Panther were supposed to prove their absolute superiority. They possessed thicker, better-sloped armor than anything the Allies fielded. However, the battlefield quickly devolved into a terrifying lesson in kinetic energy. When the German behemoths encountered Shermans armed with the new high-velocity $76 text gun firing HFA ammunition, the previously absolute confidence of the German crews vanished. Sergeant Willy Voss, no relation to the engineer. A Panther gunner recounted a moment of terror near Bastogne. His Panther was hull down, its $80 text glacis plate angled at $55 circ dollar. Theoretically, it was invulnerable to the American $75 text dollar gun and highly resistant to the $76 text dollar. We spotted a column of Shermans at about 800 meters, Voss reported. We fired first. Our round struck the lead Sherman's turret. It stopped dead. Then the fire started coming back. Not the typical clanking hit of steel rounds. These were sharp, cracking impacts, like a giant striking the tank with a metal rod. The third round hit the Panther's upper glacis plate. Instead of ricocheting, the small tungsten core punched straight through, splattering molten metal and shrapnel inside the turret. The dense core carried so much energy that it behaved like a small, hypersonic bullet. The pressure wave and fragments of the penetrating slug, often called spalling, killed the loader and wounded the commander instantly. The Panther was knocked out, not by a massive explosion, but by a precise, surgical wound. The psychological impact, the loss of the shield approx. For 3004600 words, the psychological effect of the HVAP was arguably more damaging than the physical destruction. German tank doctrine was built on the confidence that their heavy armor, a literal shield, would protect them long enough to execute their precise, powerful attacks. The Tiger I and Panther were designed to absorb hits and deal them back. The tungsten penetrator rendered that shield obsolete. Tank crews began reporting a terrifying shift in the engagement distance. Where once they could hold an advantageous position, now they knew the American $76 text dollar gun could punch through their frontal armor at distances they thought were safe. This forced the German commanders to engage at closer, more dangerous ranges, or retreat altogether. Obersturmführer Erich Kull, a veteran Tiger commander, noted the change in morale. The Americans learned to aim for the flanks and the turret ring. But with the new round, they simply aimed for the center mass and achieved penetration. We were no longer safe in our steel castles. The sound was the worst part, a high-pitched shriek, followed by the metallic tearing sound inside the tank. The round was not a bullet. It was a drill bit. The fact that the penetrator core was small and often left a clean, circular hole made the damage appear deceptively minor from the outside, but the internal chaos was absolute. The speed of the tungsten core meant that the impact energy was converted into heat and shock almost instantaneously. Back at Rechlin, Richter began to draw a profound parallel between the P-47 cooling trick and the HVAP dominance. Both were products of a singular American engineering philosophy: simplicity leading to reliability, leading to operational superiority. The P-47's ducting, simple sheet metal with a rough finish, ensured the massive R2800 engine could reliably deliver maximum power for sustained periods. This reliability allowed the aircraft to dominate the skies. The HVAP round, with its simple sabot and complex strategic tungsten core, ensured that the standard American $76 text millimeter gun could deliver maximum kinetic energy when needed. This reliability allowed the tank crews to dominate the ground. Richter realized they're complex. Precision-engineered German solutions were often brittle and prone to failure, requiring intricate maintenance and specialized materials. We seek the $100 per cent dollar solution. The perfect theoretical answer, Richter told Voss, gesturing toward the P-47 diagrams. The Americans sought the $90 per cent dollar solution, the one that worked reliably, could be produced in the millions, and could withstand the abuse of war. He noted the chilling difference. One saved American engines from thermal failure. The other delivered German tanks to kinetic failure. Technical postmortem. The kinetic energy surge approx. 4,800 to 5,000 words. The true impact of the HVAP round stemmed from the nonlinear relationship of velocity to kinetic energy. Doubling the mass of a projectile only doubles the kinetic energy, but doubling the velocity quadruples it as dollar text K propto VA dollar. By shaving mass through the sabah and boosting the velocity of the tungsten core to over $1,100. Text meters per second dollar, approximately $3,600. Text feet per second dollar. The $76 text millimeter dollar gun achieved penetration performance approaching the massive term. German $88 text dollar gun. But with lighter weight and lower recoil, the German teams attempted to replicate the projectile, using lower-grade steel cores to compensate for the tungsten shortage. But the results were poor. The lower-density cores shattered upon impact or tumbled in flight. The HVAP round was a complete system. The kinetic energy provided by the velocity needed the supreme hardness and density of the tungsten carbide to efficiently transfer that energy into the armor plate without disintegration. The absence of the strategic material meant the Germans could never truly solve the tungsten trick, just as they struggled to replicate the P-47's simple cooling trick. The enemy's engineering genius was rooted in an industrial capacity the Axis could no longer challenge, while the psychological shock of the HVAP round devastated the front lines. Back at Rechlin, Oberleutnant Richter and Dr. Voss were under immense pressure to solve the P-47's cooling mystery. The Luftwaffe desperately needed a high-performance, high-altitude fighter that could match the sustained output of the AR-2 2800. Their focus turned to applying the lessons of the American duct trick to their own advanced prototypes, particularly those utilizing powerful heat-intensive engines like the Daimler-Benz DB605 or the radial BMW 801. The problem was that the American solution was simple, but its underlying optimization was hidden. The Germans tried to replicate the precise geometry and roughness, but without the exact manufacturing tolerances and materials used by the American factories. Their attempts failed. They experimented with internal duct coatings, trying to artificially create the turbulent boundary layer that prevented flow separation. They tested abrasive grit. This fouled the airflow and caused unacceptable pressure drops. Corrugated inserts. These created too much drag and broke apart under vibration. Adjustable vanes. These added complexity and weight, negating the entire benefit of the P-47's simplicity. Richter concluded with frustration. The Americans found a sweet spot where high-speed production created an aerodynamic feature. We cannot copy the feature without also copying the process. We simply do not have the time or industrial capacity to duplicate. The inability to reverse engineer the P-47's simple genius began to wear down the German technical teams. They were a nation of engineers who prized meticulous theoretical perfection. Yet they were defeated by what appeared to be an accidental optimization of the assembly line. The contrast between the two problems was crushing. HAP. A technological defeat based on a strategic material tungsten that Germany lacked. P-47 cooling. A. Technological defeat based on a manufacturing simplicity that German over-engineering could not grasp. The American engine simply ran reliably, consistently, under maximum duress. This represented the ultimate failure for a nation that based its military superiority on the supposed quality and complexity of its engineering. Richter himself began to suffer from the intense pressure and the bleak realities of the war. He recalled flying a test model of the WWII that had suffered an oil line rupture due to constant high-temperature cycling. He had barely nursed the plane back to the airfield. The trauma of near failure due to thermal stress was a daily reality for German pilots, a reality American pilots did not share the superior reliability of the P-47's cooling system translated directly into its success as a long-range bomber escort. For the German pilots, the engagement was often one of brutal haste. They had to achieve the kill quickly before their engines overheated or their limited fuel forced them home. The American pilots, thanks to the P-47's sustained performance, could afford to be patient. They could climb, circle, and wait for the precise moment to strike, conserving their energy potential. Major Hans-Joachim Muller, a pilot tasked with intercepting B-17 formations, detailed the despair of facing P-47 escorts. The jugs were there, high above us, like hawks. We would make our desperate high-speed pass through the formation, our engines screaming and running hot. They would simply follow the curve, keep the throttle forward, and pursue us relentlessly. We would be forced to break off, not by their bullets, but by the flashing red light of our own engine. Temperature gauge. The ability of the P-47 to deliver sustained power without the engine cooking itself fundamentally altered the tactics of the air war over Europe, contributing directly to the eventual daylight bombing supremacy of the Allies. Richter finally presented his full findings to the High Command. The P-47 ducting trick was unsolvable through theoretical reverse engineering. It was a victory of the American production line over German design. Sophistication, he drew a powerful connection between the P-47 and the HVAP round. Both technologies were fundamentally enabled by an industrial machine that could produce simple, highly reliable components at an impossible scale. The HVAP round required mass production of perfect tungsten cores. The P-47 cooling trick was a byproduct of mass-producing rough, consistent sheet metal ducting. We have spent months trying to replicate a feature that was likely found by chance on a test rig and then simply never changed because it worked reliably. Richter stated in his final report, "The genius of the enemy is not in their complexity, but in their capacity to make the simple, effective, and disposable. We cannot solve their trick because we cannot afford to fail cheaply and test repeatedly like they can." The chilling realization was that the war was being lost not just on the battlefield, but on the assembly line. The cold precision of the engineering battle, the cooling duct versus the tungsten core, translated directly into the brutal psychological toll on the men fighting on both sides. For the American pilots flying the P-47, the reliability of their aircraft instilled a potent, almost religious confidence. They knew the R-2800 would not seize up, that the high-altitude performance would be sustained, and that they had the upper hand in a protracted dogfight. This mental edge allowed them to fly aggressively and relentlessly. Conversely, the German pilots lived in a state of perpetual mechanical anxiety. Every maneuver that pushed the engine to its limit was a roll of the dice. This constant fear of thermal failure, the engine fire, the loss of power, the sudden silence of the propeller was a crippling psychological burden. It made them hesitant, cautious, and predictable, further compounding the technical gap. The ground crews suffered too. American mechanics had to maintain a rugged, if heavy, machine. German mechanics were perpetually fighting the inherent fragility of their highly stressed, liquid-cooled engines, desperately trying to stop leaks, prevent overheating, and keep complex systems functioning under wartime shortages. The psychological devastation on the ground was even more profound, brought by the terrifying efficiency of the HVAP rounds. German tank crews, accustomed to the slow, terrifying grind of traditional armor-piercing rounds, now faced an instantaneous surgical annihilation. The lack of warning, the clean hole, and the immediate internal shrapnel spalling were utterly demoralizing. They knew instantly that their heavy armor was no longer a guarantee of survival. This loss of faith in their machines eroded combat effectiveness faster than any casualty count. The climax of this technical drama lay in the singular, devastating effectiveness of the HVAP round driven by the tungsten core. The power wasn't just in the velocity. It was in the incredibly high density of the tungsten carbide. To illustrate this, consider the impact energy per unit area the stress applied to the armor. A conventional steel round, when it struck, dissipated energy across a larger area, causing deformation and often ricochet. The small, dense tungsten core, however, concentrated that immense kinetic energy into a tiny point. The pressure exerted upon the armor plate was so extreme that the steel behaved like a fluid. Flowing away from the penetrator tip, the phenomenon was not simple perforation. It was a demonstration of overwhelming hydrodynamic pressure. $P, approx frac 12 rho underscore P, V, $, where $P is the pressure. $rho underscore P is the density of the penetrator tungsten being much denser than steel, and $V is the impact velocity. The combination of high velocity and high density $15.60, text gram per centimeter, $1. For tungsten carbide versus $7.85 text gram per centimeter, $3 for steel, allowed the tungsten core to cut through armor that was designed to stop projectiles. Twice its size, the American gunners didn't need to be skilled marksmen aiming for weak points. They needed only to hit the general area, and the tungsten core did the rest. This was the ultimate victory of Allied industrial capacity and strategic material access over German doctrinal superiority in armor design. Oberleutnant Richter compiled his final notes on the P-47 ducting. He and Dr. Voss had conclusively failed to reproduce the high-efficiency airflow without resorting to complex, heavy, and unreliable mechanisms. The irony was the final lesson: the simple, stamped metal duct in the P-47's wing, with its slightly rough surface and optimized, yet unintended, diffuser geometry, was a masterpiece of unintentional elegance. Richter wrote, "The P-47's trick is not a secret blueprint. It is a secret born of the American factory floor. They built it simply, they built it fast, and they built it robustly. The geometry they found, which converts velocity to pressure so efficiently, was likely the simplest design that passed their stress tests. The cost of our over-engineering is paid in maintenance, weight, and, ultimately, pilot lives." The contrast was clear. The P-47 delivered power reliably through simple, effective thermal management. The HVAP delivered decisive kinetic energy through simple, effective material application. Both were weapons of war, won not by esoteric science, but by the reliability and scalability of the American industrial base, the ability to produce simple solutions in massive quantities consistently. This was the terrifying, unsolved trick that crippled German engineering confidence. The story of the captured P-47 wing and the devastating effectiveness of the HVAP rounds converged on a single, inescapable truth for the German high command. The war was a battle not just of tactics or design, but of industrial physics and logistical reliability. Oberleutnant Richter's investigation confirmed that the P-47's sustained performance was rooted in an aerodynamic secret hidden in plain sight: the simple, mass-produced ducting that turned high-velocity ram air into effective, high-static pressure cooling air. It was a trick that could not be reversed engineered without replicating the entire philosophy of American mass production, which allowed for rapid prototyping and selection of the simplest, reliable solution. The HVAP round represented the other side of the coin. It utilized tungsten carbide, a strategic material the Allies had in abundance, to concentrate an overwhelming amount of kinetic energy onto a target. The effectiveness was absolute, rendering Germany's heavily armored tanks vulnerable. The tungsten core, traveling at extreme velocity, was the ultimate expression of material superiority enabled by a functioning, massive industrial base. The two mysteries, the cooling trick and the tungsten ghost, demonstrated that the axis failure was systemic. German over-engineering produced brilliant but often fragile and complex weapons. Allied mass engineering produced rugged, simple, and overwhelmingly reliable systems that could sustain operational tempo far beyond Germany's capacity. The P-47 simply ran. The HVAP simply penetrated. The technical challenges faced in World War II laid the groundwork for modern weapons engineering. The lessons learned from the P-47's cooling system and the HVAP penetrator continue to shape military technology today. The battle against thermal stress in aviation, a challenge that crippled German efforts, led directly to advanced cooling systems in modern jet engines and high-performance aircraft. Engineers moved beyond simple ducting to sophisticated boundary layer suction and forced convection techniques. But the core principle converting ram air efficiently into cooling pressure remained essential. The HVAP round, using the concept of a small, dense penetrator encased in a disposable sabot, evolved directly into the modern APF-SDS armor-piercing, fin-stabilized, discarding sabot round. These incredibly long, slender tungsten or depleted uranium darts are the primary anti-tank weapon used by contemporary main battle tanks MBTs like the Leopard 2 and the M1 Abrams. They are pure kinetic energy weapons, concentrating pressure and density to defeat even the thickest modern composite armor. The Tungsten Ghost of 1944 is now the undisputed champion of anti-tank warfare. The German engineers, led by Richter and Voss, never successfully implemented the P-47's cooling simplicity. The sheer volume and consistency of the American production line, the ability to turn a simple, rough metal stamping into a high-performance aerodynamic feature remained the unconquered trick. The war ended not just with the surrender of armies, but with the defeat of a technological philosophy. The complex, precision-built war machine of Germany was broken by the robust, reliable, and endlessly scalable industrial power of the Allies. The true genius of the P-47 was its ability to stay in the fight. The true horror of the HVAP was its ability to end the fight instantly. Both were triumphs of mass production, strategic resource management, and the simple application of high-stakes physics. The legacy is clear. In the crucible of total war, reliability and mass capacity ultimately proved to be the greatest technological advantages, surpassing the most advanced but rarest precision engineering. The war was won by the P-47's engine that kept running and the ghost bullet that punched through steel. A testament to the factory floor's triumph over the drawing board's ambition.